Part D, what we're doing is, we're going to take a look at an airplane and say an airplane loaded with individuals is a random sample. If we look at the weight of the individuals and their luggage on that airplane and divide that by 40, we'll come up with an average for the individuals and luggage on that plane. That average will act like this average we described in this previous part of the problem. So for random airplanes, the average individual weight will tend to be at about 210 plus or minus, depending on how you set it up, standard deviation of about 4. So that tells us how individual airplane weights are going to act. If we then multiply that average by 40, we get the actual weight of the airplane. So if we start out and say the total weight of the airplane that they're interested in is 8,800 pounds, the average individual weight is 220 on this aircraft. The question wants to know about weights that are greater than that 220 pounds. So what you're looking for is, what is the probability of seeing an average weight of greater than 220 pounds? So from this distribution, that's 210, 220 is over here. You want the area to the right of 220 on this distribution. What you can do is, you can do a Z transformation. Take that 220, subtract the mean of 210, divide it by the standard deviation, 3.95. You'll come up with a Z value of 2.53. Find the area to the right of 2.53. That's 1 minus the value in A.1 for 2.53. And that calculation comes out to be 0.0057. So that says that there is approximately a 0.6% chance that any particular airplane would have more than 8,800 pounds on board in passengers and luggage. Okay? Does that sound reasonable to you guys? If this is actual real numbers here, commuter airplanes, there's probably something on the order of 300 to 400 of these things flying over the U.S. at any particular time. So if there are, say, 400 of them, or even 300 of them, roughly 1 in 175 are going to be overloaded. So that implies to me that 2, 3, maybe even 4 airplanes are flying overhead right now that are overloaded. Does it sound so reasonable now? I hope not. I hope that their numbers are a whole lot more conservative than these are, so that there's much less chance that there will be overloaded airplanes up there. The other thing to remember is that if you're only slightly overloaded, most of the specs on these planes are set up such that slightly overloaded doesn't cause any significant difficulties. Okay, so this is a real problem. This is a real application of these techniques to a particular situation. So how do you design an airplane to be able to handle the necessary loads? Or how many people can you allow to be on the airplane? Problem number 95. I've only got a couple minutes here. Problem number 95 is trying to transition to the next piece of it. So the first one is, to draw a picture of each of the following distributions. Part A says a standard normal distribution with Z equal to 0.7. Well, standard normal is what we've been drawing right along. So Z is equal to 0.7. It's centered at 0. Extends from minus 3 to 3. We've got an area to the right. And you can look this up in table A.1. Take 1 minus that, and you'll get 0.2420. So that's the probability to the right of 0.7. Okay? If we then take the second one, which is a degrees of freedom equal to 10 and a t equal to 0.7, if we draw that, we can draw a similar bell curve. Now, personally, I would have drawn this. If you look at this, they're touching at 3 and they're not quite touching at 3. This is a pretty subtle difference. I'd have drawn it more exaggerated, so it would have been more exaggerated. But other than that, this is going to look similar. Okay? So it'll center at 0, you're going to have a value of 0.7, you're going to have an area to the right, and this value is going to be 0.2499. You've looked that up in table A.3. Since A.3 gives values to the right, you'd look up 0.7 in the table, and actually the table isn't going to give it to us. Our table that we'll add to later, we'll get there. Or you can use Excel. It tells here how to use Excel right up here for how to get that t-distribution value. You can also use a TI calculator or a number of other things. Okay. The value that you're going to get to the right is 0.2499. So the t-distribution, you're going to use degrees of freedom equal to 10. Look at that particular row, or evaluate that with that particular degrees of freedom in the t-distribution and get an area of 2.499. And notice that for this t-distribution, the probability of being to the right of 0.7 is larger than it is for the z-distribution. That will generally be true, is that the probabilities for any particular point will be larger, or the area to the right will be larger than the area to the right would have been for a z. Okay. In part C, it says to look at the same degrees of freedom, t equals minus 0.7. In that case, your minus 0.7 is down here. To use the table, what you would do is you would simply take 1 minus the area that you found in part B, because that distribution, this t-distribution, is symmetric just like the z is. So the area here is 1 minus this tail. This tail is the same as that right tail would have been. So you simply take 1 minus what we found in part B. That gives us our area here in part C. We'll have a lot more chance to work with these as we go along. On Wednesday, we'll start picking up on more of this and continue into common sense.